Hey there, this is a quick screencast to fill in details on proof of the algebraic limit theorem. Here I'm just going to run through the proof of the fourth part, the part that involves the limit of a sequence created as the quotient of two other sequences. So specifically, here's the statement. Suppose the sequence AN converges to A, and suppose the sequence BN converges to B, and also suppose the limit of the sequence Bn is non-zero. Then the new sequence, whose terms are the quotients of An and Bn, it's also a convergent sequence, and the limit of that sequence is the ratio of the limits of An and Bn. So long, again, as Bn is not, or B is not equal to 0. And this little intermediate statement is put in here just to emphasize the way we usually think about the algebra. Right? The limit of the quotient is the quotient of the limits. So let's do some scratch work. So what we're going to do is this. We're going to think of the sequence that we're interested in, this one right here, as the product of two sequences. One sequence our AN, and the other the reciprocal of our BN. And now if I can show the reciprocal of our BN converges to 1 over B, then we're done. We can use part C, as a part C of the algebraic limit theorem to conclude part D. So if I can show 1 over Bn converges to 1 over B, then by the algebraic limit theorem, part 3, the part about the limit of the product is the product of the limits, An times 1 over Bn will converge to A times 1 over B, which is A over B. Right? That's how we'll get the results. So we're going to focus on the special case of the sequence of reciprocals of Bn converging to the reciprocal of B. All right. Now remember, we know Bn converges to B, so that means that we can make the difference Bn minus B as small as we want. So I'm going to play with this expression and see if the difference Bn minus B shows up. So we want 1 over Bn minus 1 over B smaller than epsilon for some epsilon that's given. So let's play with the difference here. I'm going to create a common denominator, of course. Oh, there we go. You see it up there at the top? All right, so this is good. I know I can make this as small as I want. I know this is a finite non-zero number. So this is the thing that keeps changing on me. And this is the thing I'm going to need to exert a little bit of control over. Okay, so consider this. I'll copy this over onto this page. We want to make this thing less than epsilon. Right? Let's do that in gray. Okay. We know we can make this as small as we want. We know that this is just a finite non-zero number. So consider this. Because the sequence Bn converges to B, which isn't 0, right, if you put B on a number line, we can find a neighborhood of B where all the terms of my sequence are away from 0. That is, all these things in the tail are away from 0. They sit inside that interval. So that's what I'm going to do. And this the cutoff point I'm going to use here, I'm going to use this here. I want that to be basically B over 2. It's like right between 0 and my B. Okay, but since B might be negative, we have to use absolute values. So because Bn converges to B is not 0, there's an n1 bigger than 0, such that if little n is bigger than n1, then the absolute value of Bn minus B is less than absolute B over 2. So this means that the size of Bn is bounded above by absolute b over 2. That's the smallest it can get. So going back to our expression here, that means I can replace bn by something smaller and get something bigger. So I get this. And this is the same thing as absolute bn times 2 all over absolute b squared. So here's where we want this less than epsilon. So I'm going to multiply both sides by absolute b squared over 2. Right? And so if I can get my numerator smaller than this, then this whole thing is smaller than epsilon. But I know I can get this as small as I want. So at this point we invoke convergence again by saying there's an n2 greater than 0, such that if little n is bigger than n2, then absolute bn minus b is less than epsilon over absolute b squared over 2. So looks like we can do it. And so this is how we're going to build our proof. So how's this going to go? First, we need to explain why we can do this special case. So what we'll write is this. We'll say it suffices to show that 1 over bn converges to 1 over b so long as b is not equal to 0. If this is true, then by part 3 of the algebraic limit theorem, which talks about the limit of the product of sequences, we can conclude an over bn, which is an times 1 over bn converges to a times 1 over b, which is a over b. Therefore, we will prove 1 over bn converges to 1 over b so long as b is not equal to 0. Let epsilon greater than 0 be given. Since bn converges to b and b is not equal to 0, there is an n1 greater than 0 such that if n is bigger than n1, then bn minus b is less than absolute b over 2. It follows that absolute bn is bigger than absolute b over 2. Now we'll turn to the other control we need. Since bn converges to b, there's an n2 greater than 0 such that if n is bigger than n2, then absolute bn minus b is less than, so let's go back and make sure we get this right, is less than epsilon absolute b squared over 2. Epsilon absolute b squared over 2. So we're going to choose n equal to the maximum of n1 and n2. Then, and I'll start a new page now, then if little n is bigger than capital N, we can say absolute bn, or absolute 1 over bn minus bn is b minus bn over b bn, which is absolute b minus bn over absolute b, absolute bn. And this is less than, we'll use the first one, because n is bigger than n1. And then this equals b minus bn over absolute b squared, and there's a 2 up there. And now this is less than, so what did we say? Epsilon absolute b squared over 2, because n is bigger than n2. And here we see the 2's cancel, the absolute b squareds cancel, and we've got our epsilon. So this shows 1 over bn converges to 1 over b as desired. And that's the proof. Ta-da! See you later.